Hi guys. So for the competition, I decided to use this Mazzilli Royer ZVS driver oscillator, which is zero voltage switching oscillator, and it's based off Tinsel Koala's Tinsel Coil 7 driver. And thanks Tinsel Koala for all the tips you gave me. And really, to make these ZVS driver oscillators work, you need to understand this. That's resonant frequency in hertz, where L is the inductance in henries, and C is the capacitance in farads. And it's represented by that formula there, 1 over 2 pi times the square root of LC. By adding C, here is the circuit of the driver that I use. So plus or minus about 30 to about 69 volts. Above 70 volts it started getting really freaky. And then here's a zoomed up shot so you can see that part. And there's the primary, which is a center tap 4 gauge 8 turn primary. The diodes are 1N4006, and the MOSFETs I use are IRFP 260Ns. And as you can see there, I have it like a wiring diagram dash schematic. So, you know, the MOSFETs visualized there is like front facing. So yeah, that's about all I gotta say. Oh yeah, to adjust the frequency using that formula, when you adjust the capacitance here, the more capacitance you add, the lower the resonant frequency. You can also adjust your L, which I will show you. I'll adjust some of this, and I'll show you how I was measuring this stuff, and I'll show you my input for the Spacial Energy Cohesion Challenge hosted by Jeremy Gwilt. I never got to do all the stuff I planned, but anyways. So here is that circuit, or that wiring diagram in real life. I had this all nice and pretty, but I had to rebuild it 3 times. Twice because I blew up the MOSFETs. That's how I know 69 volts is about the max voltage. And once because I had it wired wrong. The setup is here. Disregard this coil. It's going to be used maybe in another video in a later date. But there's my 8 turn 4 gauge center tapped. Center tapped being right there. I had cut a little thing through the insulation. I measured out that's the center, and it is center tapped. And these are, well, look at the wiring diagram I already showed you. And then here, this secondary is a 21 inch, I believe it's 21 or 26 inch, 3.5 inch wide with 28 gauge wire, and it has 3 coats of polyurethane, and there's an oscilloscope to indicate wireless fields. And I have the secondary grounded. I know everybody's going to say, oh, don't do that, but I have it grounded through the oscilloscope ground, which goes to the house ground. And it's just purely because I don't want to be going outside setting this up, and that oscilloscope is already pretty much broken, so I'm just abusing it. And here's my ridiculous top load. It's friggin' ridiculous. And it is that way because my calculations were wrong when I was calculating the capacitance. It ended up the frequency was much too low, so I had to adjust the resonant frequency of the secondary via ridiculous capacitance. And now I'll show you how I figured out what frequency that I was getting. See, this is a digital signal generator and a counter, and with it I can go to function, wave, counter, external frequency counter, and then I have this plugged into external frequency to this wire, which I just hook up here. Anyways, oh yeah, the reason I have everything set up like this is because I'm doing renovations in the garage. So I have a switch that turns on this circuit. For the circuit to work, you need to have it up to a working voltage. Have these set in series. So I'm going to start it at about 40 volts. And you'll notice when I turn it on, some oscillations started happening here. Oh. Actually, I'll hook up a wire. Sorry. There's the oscillation. So I'll turn it off, turn it on. So that's at 40 volts. That the input's just over there. This oscilloscope's awesome for wireless field indication, but you can't even reliably calculate frequency. But when this turns on, I'll have you look here, 177.52. Turn it off, now it's at 0. So this thing's picking up the wireless signal. And that's how I was able to calculate the frequency I was getting. And I think the one I was aiming for was I think it was about 260 or 240. I blame it on to my inductance meter only measures 0.01. Yeah, I think it's 0.01 millihenry, which is 10 microhenry, and I ordered another one. It's in the mail. It's 1,000 times more accurate. So I'm at 40 volts, and I'll show you this. All right, so we got a little bit of wireless. Got a little bit of arcing there. You know, it's pretty cool. So that's 40 volts. Now I'm going to turn it up to 50. You'll notice the oscilloscope is getting bigger. Okay, here's 50 volts. So yeah, more wireless. And really, this is called a resonant air core transformer. But yeah, that's pretty hot arcing. We got 50 volts at an amp and a half when that's going on. And the whole system, the whole MOSFET switching system stays cold. The resistors get warm, but the MOSFETs themselves stay nice and cool up till about 70 volts, 75. So now I'm going to put it up to 60 volts. Okay, we're at 64 volts. It's pretty cool. I like it. I like these ZVS drivers. Lets you pump in a decent amount of energy into whatever you're trying to pump. I usually see them with flybacks or iron core transformers or ferrite transformers, but this is just like a resonant air core transformer that looks a lot like a Tesla coil with a funky friggin' top load. But yeah, so now I'll show you at 65 volts the wireless range. Watch the dog. So I can't really show you, but just take my word on it. It's a solid 5 feet. At like getting it there. If I turn out the light, you see it more. It's a solid 5 feet away, and I was planning on building LC tank circuits with variable inductors, but yeah, I couldn't get them to work, and then I was having trouble with getting the circuit going, and just, you know, everything is takes so much time, and I got just so much stuff to do. So I don't want to complain, but I'm going to carry on with that. I wanted to use an LC tank circuit to power a wirelessly pickup tuned into this resonant frequency, and fill up a cap bank, and then use that to run a Slayer exciter, and then do the same process over again. That was my big plan, but it just didn't get there. I just didn't get to that point. But I got to this point, and I'm pretty pleased with it. So, like, awesome work, guys. All of us who are doing this, the wireless challenge. And yeah, that's pretty much the whole of my video. And I appreciate you guys, you know, working on all this stuff, and we'll carry on. So peace, guys, and yeah, till next time, have a good one. Later. So here is one of the LC tank circuits for tuning into the wireless field that I was working on. This one's made out of 22 gauge wire. Here, that's just a capacitor I threw in to show you the idea. Here is a that's welding iron, soft iron welding iron, and it goes through the core, and it changes the inductance by quite a bit. But I have a feeling that I need to do this higher quality. That's 22 gauge wire wrapped around a pen and then epoxied. I just have a feeling that I'm gonna nail this. I just need to work on it more. Yeah, I built a couple of these, and one with the variable air capacitor. I just couldn't get them to work, but this is something I'm going to continue to pursue. When you get these going, I believe you put a full bridge rectifier across here, then you can put capacitors there, and that's how you can convert wireless energy into usable energy. And I was going to use it to drive a Slayer exciter, low power, from a high power unit. But anyways, I just wanted to show you guys that. And I'm going to show you some more stuff. Yeah, the capacitors I used in this setup are these vintage Soviet era 1000 volt 10 nanofarad or 0.01 microfarad silver mica tuning capacitors. I ordered these. I think they came from Russia or the Ukraine. I just thought they were cool, so I ordered them. Just thought I'd throw that in there.